start. So, some informal announcements here. There is a WhatsApp group that we have created to facilitate communication between us. Also, if you want to discuss anything about social activities, there is our informal social coordinator here, Emmanuel Teixeira, who is always helping everyone engage. And also, there will be a group picture in the first coffee break on Wednesday at IFT, okay, in the other institute, where we're going to have the continuation of our event. I would like to say as well for everyone that this event is quite broad in area, right? So physics of life, as you know very well, encompasses many different things. So please don't be shy, don't feel ashamed about asking questions. It's completely normal that none of us will know all of the other areas. So please feel encouraged to ask questions whenever you want. Also, I would like to discuss about exercises. So there will be exercise sessions in the end of the day. These sessions will take about 1.5 hours. There will be 3 different rooms available here and then at IFT per day, corresponding to the 3 different courses that we have each day. Okay, so each of these rooms will be for a different course, and you go there, try to do one of the exercises that the lecturer has assigned. If the lecturer has not assigned any exercises, you can go there to study the course or ask questions to the lecturer. He or she will be available there. Okay, so we expect you to do these. It's part of the school to work hard in these sessions, okay? What else can I say before I start? Well, other than that, if you need anything, please let me know, or any of the other organizers. Before we start, we actually have 2 videos, one from Principia and another one from ICTP-SAIFR. So I think you can play the videos.
O Instituto Principia é um centro de produção e difusão do conhecimento científico e de conexão da ciência com a sociedade. Com atividades científicas desde 1951, tem atualmente 3 programas de atuação relacionados à pesquisa, educação e divulgação científica. No programa de pesquisa, acontecem eventos internacionais sobre temas atuais para diversas áreas da ciência. No programa de educação, a Escola de Talentos oferece oportunidades de desenvolvimento pessoal e acadêmico a jovens que tenham grande interesse e altas habilidades para a ciência, oferecendo uma tutoria científica com pesquisadores renomados. No programa de divulgação científica, existem diversas atividades com ênfase para o público jovem, como o Youth Science, o cinema científico e publicações em várias redes sociais. Conheça, participe, amplie seus horizontes através da ciência. www.institutoprincipia.org.
Okay, that's great. So let me thank everyone involved in the organization of this event, the staff and all the researchers involved. And now, without further ado, I would like to introduce our first lecturer of the first course, Professor Gabriel Mindlin. He's a professor of physics at the Universidad de Buenos Aires. His research focuses on nonlinear dynamics, and in particular the physical mechanisms underlying the production of songs by songbirds. Please, Gabriel, the floor is yours. Thank you very much.
Thank you very much. It's a pleasure to be here. Thank you to the organizers, to you for attending. And Nathan, it's always wonderful to be back in Brazil, in São Paulo, and particularly at ICTP, that does so much for research in basic areas in Latin America. So please enjoy this experience, create bondings, and those are maybe the backbones of future collaborations when you are peers and you meet again in your careers. So I'm going to be talking in these three classes about, I think that the title was Artificial Intelligence and Dynamical Systems Applied to Biological Systems. That was the name of the talk. And the hypothesis when I decided to build this course was the perception that, well, the strong feeling that I have that the main decision that the people in your generation will have to face when starting a scientific career is not whether you are going to be a theoretician or an experimentalist, or whether you are going to be working in South America or in Europe or in the United States, or you are going to be working on field theory of condensed matter, but which is the degree in which you are going to be using what I am going to be calling interpretable science with respect to what we're calling artificial intelligence, data science in general, in a wide sense that I'm going to be describing in the following lectures. What I mean by this is that in interpretable science, the variables that we use have meaning. We know what we're talking about. We decide that we want to explain a phenomenon in terms of variables that we understand. And we create a relationship between the different variables that are interpretable in terms of some mechanisms that we want to unveil. And probably if you are sitting here, it's because you were curious about nature and you wanted to understand exactly that, which are the mechanisms that are responsible for some phenomenon that you want to see. But probably you are getting tempted all the time to jump from academia and go and work to an enterprise or a company that maybe does research related to scientific ideas, where the dynamics is completely different. It's a completely data-driven science where complex, non-interpretable models, like neural networks, are trained with examples, and the model does not share with us the rationale behind its success. So maybe this is a caricature, but it's not a bad caricature. So many times, and many techniques, maybe many techniques that you're using are related to these mechanisms. Why? Well, it's very simple, because usually with those techniques, you can face problems which are much more complex than the ones that are plausible to be modeled by interpretable mechanisms. But there is a price. So this is not going to be about trying to convince you of one approach with respect to another one, but I want to share with you some examples of my own research where I'm using one or the other, or I'm informing one with the other, or I'm trying to unveil why these mechanisms are capable of unveiling the rules of interpretable model. So what I want to share with you is the examples of different aspects of this. I want to share the power and the limitations of each of these approaches. So the basic structure of this little course is going to be today mostly about dynamical systems. At the very end, I'm going to be talking a little bit about some neural network models, and then the two other classes are going to be more focusing on these new techniques. So the discussion is not completely new. If there is a counterpoint that is illustrative in this regard, is the dialogue that, of course, never could exist between Kepler and Newton, because Kepler died when Newton was still not alive. But basically, it's a counterpoint that is very actual today. No? So Kepler unveiled a very important problem in science, and Newton did something completely different. He unveiled the rules that could explain the behavior that Kepler phenomenologically unveiled. It was so fantastic, this mechanism that Newton presented to the world, that for some people like Laplace, when Laplace got familiar with Newton's work and returned to Europe, he said, this is the world system. All we have to do is find the force in a problem and then measure some initial conditions, and the future is going to be always predictable for any system, if you want. So it was like an explosion, a conceptual explosion that affects us all the time, even now, of course. The contribution of Newton, without doubt, is one of the most important in the history of mankind. So why should we mind and describe a problem with differential equations? Should we? Can we? Because after all, as we said, you can do data science, like the one that Kepler did, and solve one of the biggest mysteries for mankind for, I don't know, 2,500 years. People have been wondering about the nature of the dynamics of the errant planets, and Kepler, without understanding a mechanism, could, unveil these rules. And although the variables in Kepler's law are interpretable, there is no interpretable mechanism underlying them. And of course, what Newton did is something completely different. We're going to review some high school physics here, but basically he defined the velocity, and he said, well, if there is no interaction between a particle and the universe, everything is going to remain the same. When there is going to be one parameter that tells us which is the intensity of our interaction, and all you have to do is unveil a functional form describing the variables, position, and the velocity. Then you measure the initial conditions, and this is another wonderful contribution of Newton. He developed calculus. So for this system, if this force is smooth enough, you have to measure only a finite number of numbers, finite number of initial conditions, and then the future is unveiled forever, okay? Just like a bonus, he unveiled the gravitational laws, but of course this paradigm also works if you have phenomenological forces. Whoops. So to perform a prediction, all you have to do is to take the variables that you can interpret, relate them by some functional form, and once that you have this force, you can predict the evolution of your system. But here's one of the big powers of having a mechanism. You can unveil this as a function of the parameters, and what you can do is to explore the model beyond the region where this model was unveiled. So for example, you can be unveiling the laws of the universe, the laws of motion, by looking at ellipses, but then you know that if the energy is higher than some value, then you will not see the comet ever again, okay? So the idea is that when you have mechanism, you can go beyond where you use the data to unveil a model, okay? Of course, this is not exactly a law. This is a whole program of how to do science. You measure a finite set of initial conditions. You try to elucidate the laws that are relating the variables. You integrate the ODEs and you make your predictions. And of course, this can be used not only in very simple systems. You can use it in phenomenological models. We're going to be using them in neuroscience today. And in principle, it's a wonderful tool to try to understand and compare your predictions with the natural systems. Have in mind that, of course, this Newtonian paradigm doesn't work, for example, for equations with delays. If you have equations for delays, you cannot have a finite number of initial conditions that determine uniquely the future of your system, okay? You measure one initial conditions for this one variable problem, and you need also the delayed variable to make the prediction, but then to move a step forward, you also need the previous condition and also the following delayed coordinate, and therefore you need a continuum of initial conditions. So this is an infinite dimensional problem. So Newtonian dynamics, for example, doesn't include electromagnetism. In life sciences, this is a big thing because systems with delays sometimes are not so easy to avoid. Anyways, in dynamical systems, that is the, if you want, the hardcore of interpretable dynamics, typically you look for a description in terms of an ordinary set of differential equations that means a finite set of ordinary differential equations. And if you know that the function, if derivatives are smooth enough, then you have for each initial condition a unique solution. And in general, dynamical systems tries not to find analytical solutions for those, but more talk about the qualitative changes that you can have in these basic elements of the description of the dynamics for different values of the parameters. So the language of dynamical systems typically is to try to identify these elements, like, for example, fixed points, limit cycles, chaotic attractors, and try to see if you can prove the existence of those sets by qualitative or geometrical arguments. So you know that unless you are working with a harmonic oscillator or, wonderfully, gravitation, Newtonian gravitation, basically you cannot solve analytically your differential equations. So typically dynamical systems gives you a way of geometrically saying something about the set of differential equations that describe the relationship between those variables that you have attached some meaning to, okay? So for example, the typical example, the relaxation oscillator, you cannot find an analytical solution for this. Are you familiar with this? Okay, who is not familiar with this equation? Okay, very briefly, imagine just this and this. This is the harmonic oscillation, okay? And this is going to be some dissipation, which is going to be a negative dissipation for small value of the variables and a high dissipation for high values of the variable. That means you put energy when, near the origin of the system, and you dissipate it for large values of the variables. So you make some change of variables. I'm not going to be describing this in detail. I just want to give you the flavor of what kind of tools dynamical systems use to solve these problems. You make some change of variables, and you transform this equation into this set of differential equations. You look for values where either of these equations is equal to 0. This defines curves, which are called nullines. And then, looking at the relationship between these nullines, you can infer that you have some phase collapse to slow regions and some fast collapse to high regions, and so on, and prove geometrically that you have a limit cycle in these dynamics. By the way, I took this image from the internet, and yesterday when I was checking the presentation, I found that there is a mistake. This thing should go to the right of the red curve, and this to the left of the red curve, and in the problem session we can discuss why, okay? But anyways, this was just to give you a flavor that in dynamical systems, many times you look for qualitative description of the dynamics with geometrical terms. This is what I call, to the disgust of my neuroscientist colleagues, the proof that this is the Newtonian description of neuroscience. Okay, these are called the Hutchin-Huxley equations that deserve the two authors a Nobel Prize in the 50s, and describe the dynamics of some variables that are basically for the activity of a neuron, okay, the voltage between the inside and the outside of the neuron, and these variables that describe the opening and closing of channels, and describe these wonderful dynamics that neurons have, where in principle they are at equation state until you perturb it beyond some threshold and you have a huge spike. And I say that this is the Newtonian version of neuroscience because the assumption here is that after Ramon y Cajal, we know that in principle a brain or a nervous system is built by these particular neurons, which are cells. The dynamics of them can be described in terms of their voltages, their degree of polarization. And you're claiming that the dynamics of each of these can be described by a finite set of differential equations. So the fantasy would be, well, I put them all together, I connect them, I measure the initial conditions, and I can understand when you're going to be, I don't know, getting up and leaving the room. But just if I could measure the initial conditions. So, of course, we know that we have too many variables. We know that this is a caricature, but this would be like the extrapolation of the Newtonian philosophy to neuroscience, a Newtonian approach to neuroscience. So I'm going to be describing a dynamic and systems approach to the problem that I'm interested in, or I've been interested in the last 25 years, which is the physics and neuroscience of birdsong production. Just let me give you just a couple of comments of why I find that problem interesting. The reason I find it interesting is that learning is a very complex phenomenon that affects us all. We all want to understand the problem of learning, and learning complex behavior, it's fascinating, and one of the most fascinating behaviors to me is language and vocal communication. And it's very difficult to understand that in humans. Birds, there are 10,000 species of them, but 4,000 species, which are docile birds, share with us that they need to be exposed to a tutor in order to learn. That means that their brain has some basic structure that is genetically built, but then through experience, you start to change some of the connections and you learn a new behavior. So this process of learning can be understood in birds much easier than in humans because birds have some neural structures that are dedicated to some production, and you can go and measure them. And one of the aspects that I found it very interesting is how much of this complex behavior is determined by the brain and how it is conditioned by the biophysics of the song production. So today I'm going to talk about dynamical systems in terms of the physics and the neural aspects of birdsong production. So today is mostly about dynamical systems. And tomorrow and on Wednesday is going to be about artificial intelligence. So let me give you in 2 seconds what I've been working the last 25 years, which is kind of depressing to me. But anyways, so this is a song, this is a cardinal. And they produce this song with this mechanism that is called the syrinx. This is a bipartite structure. You have labia here that are similar to the vocal folds. So now the bird is breathing quite normally, and the vocal folds are quiet. But at some point, you're going to put them together, and when the air passes through them, they're going to start to oscillate. When they oscillate, you are creating a flow that is modulated, and the sound is generated by the rate of change of the rate of mass injection in the trachea. Okay? So, if we want to model this in terms of a dynamical system, I'm going to be doing some history because this work I did many, many years ago. This is what the biologists tell you about the syrinx, this vocal organ. You have the labia hidden in here, attached to this annuli here, and through these muscles, you might compress them and stretch this labia, and when you stretch this labia, the restitution constant is going to be higher for this labia, and they're going to be oscillating faster. So one of the ways in which birds control the frequency of the vocalizations is going to be by changing the activity of these muscles in here. And also, they have to send some important amount of air, okay, in order to blow in between these labia and make them oscillate. So the parameters here are the pressure and the tension of this labia, basically. So here you have a picture of this lateral labia, whose dynamics I want to model, because those are the ones that are going to be modulating the flow, and therefore the sound production. So I have parameters, which are the pressure here, the tension in this labia, and I want to understand the dynamics of those labia. Now, when I started to do this, I couldn't look at them. Now I can, and now I have techniques to unveil the dynamics directly. But at the moment, it was a conjecture, which is typically what happens in life science. Okay, of all the variables that might be relevant, most of them you won't be able to measure them. And the fantasy is that you're going to be making a low-dimensional system which is biologically pertinent. And this, I couldn't stress it more, because if you're going to be interacting with biologists, and you come from a physics or math background, so let me ask you, how many of you are biologists? It's just a small number of people, right? Most of you are physicists. Exactly. So get used to it. If you're in this business, these guys in here will tell you what you say is bullshit. It's too simple. It's too simplified, okay? So how to test the pertinence of this is actually very, very important, okay? So let's do the exercise of trying to see how you can go about doing these kind of things. So this is the same picture, but done by a physicist. You can see the difference. Those are usually much more pretty, much more, and these are more simple. So the idea here is that you have this dynamics in terms of a variable that I want to interpret, which is the midpoint position of the labia. And then you're going to be creating some pressure waves by looking at the rate of the flow here. And you're going to be traveling through some trachea and then exciting an oropharyngeal cavity, and then you're going to be exiting. And the dynamics here is highly nonlinear. So let's try to build a low-dimensional model for this. Okay. This is strictly a Newtonian problem. So I'm trying to see which is the dynamics of the midpoint position in here, and I write the equations of motion, like the derivative is equal to y, and the forces are the restitution force, the dissipation, nonlinear dissipation, because these labia can collide with each other, okay? Collide with each other or with the containing walls. So when they are far away from the equilibrium position, they are going to be losing a lot of energy. So this is the nonlinear dissipation. And this is a calculation that you can do, but using some typical flow dynamics in between two modes that are activated. So you conjecture that you have two modes, a lateral mode and a wave-like mode. You can put the average pressure in there, and you get this formula, which is kind of nasty. And the way in which you understand this problem using dynamical systems is not by trying to hope to find an analytical solution, because there is no hope in there, okay? But what you do is what I'm displaying here, that is called a bifurcation diagram. So doing dynamical systems is basically computing bifurcation diagrams. That means of your differential equation, trying to find the regions in parameter space where the dynamics is qualitatively different. So which are the parameters? We mentioned them already. The tension of the labia and the pressure of the air in the air sacs. If the pressure is high, there is going to be a flow of air, and you're going to be having oscillations. And if you're having oscillations and the tension is high, the oscillations are going to be higher. Make sense? Okay, so when you look at the different regions in parameter space where you have the different behaviors, of course, if the pressure is very low, there is going to be no sound, because there are going to be no oscillations. And when the pressure is high, you're going to go into a region where you have oscillations, because you are putting energy into the system that is dissipated outside and stuff. And in all these different regions, there are little qualitative changes that are called bifurcations. And it doesn't matter exactly if you are here or here, or if you are here or here, the dynamics is qualitatively similar. And actually, I think that this is why we can do physics at all. If things would depend dramatically on the particular values of the parameters, we would never be successful in modeling anything, okay? The idea that you have wide regions in parameter space where the qualitative is more or less similar is what gives us hope of ever doing some successful phenomenological adjustment of any problem, right? So for example, these different colors are what are called different bifurcations, different ways in which the flow can change. This is called, for example, a Hopf bifurcation. A fixed point loses stability smoothly and gives rise to a limit cycle, which is harmonically very poor because it's just an oscillation. In here, for example, you have 3 fixed points. This is a saddle, this is a node, and this is a repulsor. So in principle, you are at this state in here, but if when you change your parameters, these two collide, what you have is that the unstable manifold continues in here and you create another oscillation. But now the oscillation is qualitatively different because you stay a long time in here and then you have like an explosion, okay? So these two ways of turning oscillations on give rise to qualitative different sort of oscillations. One that is harmonically very pure and the other one that is like huge explosions. This to me is very important because the sound that you will create with one thing or the other is qualitatively different. So in the exercises today, we're going to be giving you some codes to integrate dynamical systems, and we're going to give you this system so you can change your parameters and get familiar with bifurcations if you haven't worked with those. Anyways, this is the utmost success of dynamical systems, is what you want to do if you want to model something in terms of a low-dimensional dynamical model. Not get lost with your first model, because it's going to be full of parameters and stuff. This is called a normal form, and this is the simplest differential equation that is compatible with some particular model, with some particular linear degeneracy. So if you look at this equation, it has has less terms, and they are only polynomial, okay? And there is an algorithmic way of changing your equations into these simpler equations. And the interesting thing is that you are guaranteed that the qualitative behavior that you're going to have is exactly the same. But of course, now your parameters are much less because you eliminated many terms, and now you have a dependence only on the temporal scale, the sign of these terms, and then the parameters that you control. Always, when you look at a phenomenological model, invest some time in computing the normal form, because I assure you that there is some Russian mathematician that has already studied this normal form. So you can map your problem into a problem that has been thoroughly studied by some hardcore mathematician. So by just the price of knowing how to do this change of variables, you gain all the rigor of math that is 100 years solid, okay? At this point, I don't know whether you are finding this trivial or completely crazy, so let me stop for a minute and take some questions. Yes?
I don't want to play the devil's lawyer here, but what actually is the control of the animal on these equations?
The what?
The control of the animal in these equations. Like
yes.
Because this is completely autonomous, and I would expect
wonderful
that it's
question. Wonderful question. So the control of the animal comes in this parameter, which is the pressure, basically, and in this parameter, which is the tension. So basically, before you're creating these big pulses, what the bird is doing is having an autonomous clock that has a pressure going up and down, and you have a normal breathing. But you have to go beyond some level in order to create the sound. So you have an autonomous oscillator, and we're going to look at it in a moment. You're going to be having an autonomous oscillation that is creating the normal respiration, and actually Facundo here works on that, the normal respiration of a bird. And when the bird wants to sing, it has a telencephalic set of nuclei that take over and say, like, give me just a few seconds of your time, and I want to create larger pulses because I want to create sound. So the first thing that the bird does is to hug with telencephalic nuclei, these respiratory nuclei, and generate these huge pulses. Now, when you set up these huge pulses, you have these autonomous oscillations that you see. But you have to have the parameter beta into this region to have these autonomous oscillations. So the bird is not controlling the actual motion of the labia, it's just putting the pressure in a region where you have autonomous oscillation. You are blowing hard enough so that you have these two pieces of paper oscillating autonomously for that value of the parameter. And the other thing that the bird control is when you put yourself in that regime, you can make the tension higher or lower and sing or, okay? So you have control of this variable. Okay, here is a problem because alpha is the pressure, sorry, and beta in this scheme is the tension, but it is putting alpha in the region where you have the oscillations and beta in the region where you have high tones or low tones, okay? So these are the two parameters that you control. Once that you are in a region of parameter space where you have oscillations, the oscillations are autonomous. Okay? Wonderful. Another one? You? No? Okay, here.
So yeah, where does the learning that you said earlier comes in place? Like, what does the bird learn and how to module his vocal cords?
Beautiful thing.
Do you model those? Or
Yes.
This parameter has something to do with that?
Yes. During the 3 courses, I'm going to be talking about exactly that. What is the part that is learned and what is the part that is genetically programmed? And basically, one of the ideas we're converging to is that even if there's learning, all you do is to combine elements that are genetically pre-programmed. But we'll see when we go to the brain aspect of the talk. Fair. Okay. Another one? We're fine. Okay. So, yeah.
All birds have essentially the same morphology.
Beautiful.
What exactly changed? What do you change in the model, and what
Perfect.
exactly?
Perfect.
How you compare things?
Okay.
And how you generalize?
Yeah. So there are 10,000 species, and there are 4,000 that learn. In the 4,000 that learn, the anatomy is basically the same. And all you can control is whether you are using more Hof bifurcations and creating more tonal sounds, or you are going to more creating solenoid limit cycle bifurcations that have rougher sounds, or combine them. So basically, in those 4,000 species, all you do is how to control the same basic structure. But then you have another 6,000 species where there is no learning involved. And in those, it's not about the control of how to operate this machinery, but you create different structures. So for example, sabocines have, for example, tracheophones have 3 sound sources. And then you have other species that have other settings with just 2 labia, and they create sounds with those 2. And in some species, those 2 are asymmetric, and you generate rougher sounds because the 2 labia are asymmetric. So you have 4,000 where the structure is very well preserved, and another 6,000 species where each species is completely different new physics.
Parrots and things that have very complicated sounds, then would be a completely different
And that's a
system.
completely different thing. And they have tongues, and that's a completely different talk. Parrots are another thing. So learning happened 3 times in avian evolution: oscine birds, and then parrots and hummingbirds. And parrots are something else. And the brain structures are different and stuff. But I'm not talking about parrots today or tomorrow. We can talk in the coffee break about parrots. Okay, so the normal form reduction, and I cannot insist more, if you are ever going to be using dynamic systems, go and learn this, is how to prove, how to take your dynamic system that is phenomenological and depends on your talent and your director advisors prejudices and so on, and take that differential equation, take it to the normal form, and then use the normal form to understand your problem. I really encourage that. It's much easier to understand the dynamics of a problem with less parameters than a problem with more parameters, of course. And for example, related to what you were saying, if you want to generate a tonal sound, like a canary, for example, you can start your oscillations here. So when you want to start a syllable, you go here, you have a tonal sound. And if you want to create something that is rougher, like a zebra finch, something like that, then you start your oscillations here, where the basic oscillation has a more spectrally rich behavior. And some species can alternate between these things, and some species live more here, some species live here in parameter space, and so on. Okay? As I was saying before, for example, a Hopf bifurcation is a bifurcation where this point loses stability and gives rise to this very, a very tonal limit cycle. But here what I'm displaying is how when you collide these two, okay, this unstable manifold, that is the stable manifold of the node, becomes, after this Sutherland node collide, to a unique limit cycle, but here, traveling much slower because you have the fingerprint of this bifurcation, and then you have a rapid oscillation and a slow transit in this region and so on. So for example, the Sutherland node in a limit cycle bifurcation is one of the ways in which oscillations can emerge. The good news is that you don't have that many different bifurcations, okay? So it's not that you are going to have, 200 bifurcations. You have 3 kinds of turning oscillations on in 2-dimensional dynamical systems, okay? So this is the kind of thing that if you learn normal forms and bifurcations, can simplify your life. If you want to study this subject thoroughly, you have 2 doors which are qualitatively different. It's like the red pill and the blue pill. You have to choose which of the 2 you want. This is Steve Strogat's Nonlinear Dynamics and Chaos. This is happiness, because you read each page and you feel you understand everything, okay? Well, because Steve Strogatz is a very brilliant mathematician and also a brilliant teacher. And also someone that knows how to make you happy. So it's all the combination of things. So if you're not a mathematician and you want to have a good idea of what dynamic systems is all about, this is a wonderful introduction. Go and read this. This is a pleasure to read, something you can read by yourself. You self-train on that, and you have problem solved and so on. This is a trip, beautiful trip to understand nonlinear dynamics. Now, if you want to work on nonlinear dynamics, there is the other pill. This is Guggenheimer and Holz, Nonlinear Oscillations, Dynamical Systems, Bifurcations, and Chaos. It's a very hard book, but it's very deep, and you learn a lot. One thing that you cover in here and you don't cover in here is, for example, normal form theory, okay? Then there are many other interesting books, like Devani and Smail, who won a Fields Medal, has a beautiful book with Hirsch and Devani, which is an equilibrium between the 2. But these 2 are like the 2 paradigmatic ways of entering this field. Now, pertinence. This is something that when you work on the physics of modeling a biological problem, these people in here are going to be teasing you about all the time. How to test whether your model is good enough or not. So let me give you a very simple example that can be modeled by very low dimensional dynamics. This is the song of a bird I'm going to be talking about in the workshop. Okay, this is the song of the cingolo. You have the cingolo here, it's the Sonotrichia capensis, and if you go to the parks in here, you can hear it. It's a bird that learns the song, but each bird learns only one song. The 2 first syllables are the theme, and this is the trill. The trill is dialectic. Since they learn it, in different regions, they have evolved to have different trills. So probably the Sonotrichia capensis here that you will be listening to in the park, okay, here, are going to sound a little bit different because they have accents. Just like people in different regions of a country have different accents. Well, these people develop different accents, so here sound a little bit different. And actually, for those more experimentalists, we can do an exercise where we can record Sonotrichia capensis in here and compare the different dialects, okay, with the ones in Buenos Aires. And this is the model of a low-dimensional dynamical system. The other sound, please. Guys? Okay. And this one here. Okay, this wasn't tuned, so you see that it's more mechanic, but it's the kind of thing that you can start to try to iterate over to see whether they like it or not. And how to know whether they like it or not? Let's try to see this one. This is a bit more complicated. This is a zebrafinch. Can we hear to this and this, please? Okay, that was difficult, right? Let's try it again, the same one. Okay, this alternates many different sounds, more tonal, more rough, more spectrally rich. It goes to the half bifurcation, to silent note and limit cycle. Let's try to see the modeling of this. The one below? Okay, so now the two together, please, sorry. Okay? Okay. Well. So one way in which we wanted to test whether this low-dimensional dynamics was reasonable or not was to ask a bird whether it would confuse a song, his own song, with a synthetic sound. So we took birds. Anna Amador, who will be in the workshop in the weekend, she was a neuroscientist in the University of Chicago. She would measure in some auditory nuclei of the bird the neurons that are selected to the bird's own song. So in order to be creating all this learning, you have to have regions of the brain that react to your own song. So those are neurons that if you hear the song of someone else, won't react, but if they hear their own song, they're going to be reacting. So what we are seeing here is when we play this song, the raster plot, that means the responses in time, okay, in different experiments, okay, and each point here is a spike of a neuron, and you see all this accumulation of spikes because the brain reacted to the song. Wonderful. Now, if we play the reverse sound, that means the same song, but backwards, so you have all the same sounds, acoustically, the same elements, but you play them backwards, no? Like if I start to read backwards a word, then you have no response at all. And if you play here a kind of specific song, so this is the song of another member of the species that lives by it, there is no response. Now if we play the synthesis of the low-dimensional model, which is this one in here, okay, you have responses similar to the bird's own song. So if you are so kind, can we play this and this together? Okay. This was interesting because I'm showing you the successful experiment, but at the beginning we failed miserably. We had to tune exactly the parameters in order to achieve this and include some effects that we weren't including before, like, for example, some level of noise in the muscle activity. We have to take into account, with a lot of precision, the upper vocal tract, things that then are plausible to be interpretable in evolutionary sense. Why some variables are crucial. And if you mess up with those, you have no response, even if to our ears they were identical songs. So to the question of, is low-dimensional dynamics good enough? I can say yes. Is it informative? Yes. Do you learn by knowing which parameters are important? Yes. But you cannot just play around a low-dimensional dynamical system and hope that it's going to be biologically pertinent. Unless you use it to generate knowledge with experiments, you can do bullshit very easily in this field, okay? So this is like a kind of a warning sign. capensis in the field. This poor guy had to learn during very many months a song, but it learns only this song. This is the only thing that does. It sings only that. And we wanted to test whether for these guys, now in the field, it was a threat to listen to a synthetic sound. So this is the work that we had to do in the pandemic because we couldn't go to the lab for 2 years. So we went to the field and tried to do something in the field because we had many students doing experimental work. They had to do some credits in experimental work and we couldn't go to the lab, so we went to the field. So we started to follow the learning of these birds. So here we have a tutor that is singing here, and it has the complete song because it's an adult. So it has the 3 themes, it has all the trill. And in the spring, these little juveniles go like to school. And they go to school, and every day they go to these specific trees, and they sit in their banks, and they listen carefully, and they try to practice. So here we have these juveniles that are practicing together with the tutor, and here you see this. They still cannot generate the trill, they only generate the theme, and it's kind of shaky and stuff. So the way in which we do it, we put 2 microphones here, 7 meters apart, and we measure the time difference of arrival of the sounds, and we can unveil which is the exact position of these birds, and then you can see where you have the tutor, where you have the students, and how repetitive it is. And it's very repetitive. Here is what the different themes look like in the park, okay, in the region of 1 hectare approximately. So you have all these different themes. So you have many individuals that are singing this song, many individuals that are singing this, many are singing these themes, so they're very similar. And I'm going to be talking about the cultural evolution of this over several decades in the talk for the workshop. And this is the synthetic copies of these songs. So what we wanted to see is whether they would consider these songs real threats. So what we did during pandemic is we went to the field, we generated the synthetic copies, and we built these robots that were doing playback of these songs. So when you put a robot in the territory of a male that is protecting the territory, they will start to sing faster. Okay, they are trying to intimidate the invader singing faster. So what I'm showing here is the rate of production of song, and these birds are generating some songs, and when you play the song of another species with a robot, basically they don't change the rate of production of their songs. When you have a real song, and you put a robot to do playback of a real song, they will start to sing faster, and you play just for this amount of time, and then they will relax, and eventually, like 10 minutes later, they're going to be singing at the same pace that they were singing before. But if you hide a synthetic copy, what you have is basically the same response, okay? If you do a test wedge, what you see is that the response is identical to synthetic songs to real songs. And this is the kind of tests that you can do in order to find whether your low-dimensional model is behaviorally pertinent or not. Could a neural network get to be that good in generated fake copies? And this goes to the heart of the moral of the tale of the course. Because many people ask me, why do you write a model to generate a synthetic sound if you can make a neural network or use artificial intelligence to synthesize a good copy? Who wants to answer to this argument? In what sense, what could be better trying to model this aspect than doing a copy with artificial intelligence? What kind of questions can I ask with this that I cannot ask with artificial intelligence? No wrong answer, just guesses.
model interpretability.
Interpretability. And that's exactly. And what kind of thing can we ask since we have interpretability?
I believe that alpha and detention, beta, are the key important parameters. So if you train a neural network, you won't be able to learn about this or interpret these values.
Yeah. Okay. Fair enough. Something else? Someone wants to add something? For example, I can ask, what was intimidating about this song? Maybe if the pressure goes higher, if the model simulates that the bird is larger, maybe if it's more skillful, if it sings more syllables per note, if I can start to change the parameters that I can interpret in terms of what they mean biologically, what is more intimidating or less intimidating? For example, what is a sexy syllable for a female? I can copy a male, but what did she like about this male? Can I make it sound sexier? What is sexier? And which is the parameter that controls the sexiness of the bird. So these are the kind of things that if you do interpretable dynamics you can play with, and if you do artificial intelligence you can't, even if the copy may be better with artificial intelligence. I don't know, questions for discussion. This whole course is going to finish with a discussion, so plan your refutation of my arguments during these days at ease. Let's go to the brain. How they generate this alpha and beta, how they generate the things that they control. These are the set of nuclei in the brain of a bird. They have two halves, and this region is the telencephalon. They have a nucleus called HVC. There are several hundred thousands of neurons in there, excitatory and inhibitory. They go to another nuclei that is RA, that is separated in a ventral and dorsal region. In one of these regions, you feed the neurons in nucleus N12. Nucleus N12 projects directly to the syringeal muscles, and that is how you control the tension of this labia. And this is one of the things that you control, that you were asking. And this is the other one that goes to the respiratory nuclei. You have RAM and PAM that are generating the inspirations and the expirations. And normally they are having these oscillatory dynamics, and then suddenly you hack them, and you create larger pulses of pressure that are going to be putting this oscillation in this autonomous regime that your classmate was mentioning. Then you have a feedback loop, DA move, and so on. And this is just the sound production. Then you have the anterior forebrain pathway that is another set of nuclei that compares the auditory part with what is generated and sends error signals that are going to reinforce these connections, altering the architecture and therefore the shape of the instructions that you generate. And when you look at this, you say, is it there any hope on Earth that you can find a low-dimensional dynamical system to model this mess? This is a fair question. Each nucleus, we know that this has excitatory and inhibitory populations, and the way in which we experimentally measure this in our lab for the last years, 25 actually, so we've been measuring the tension in these muscles, the pressure in these air sacs. You can ask, for example, Facundo about that, because he's been doing that for his PhD thesis, for example. So in here you have a bird that has a cannula in the air, going to the air sacs, and this cannula goes to this chip where you have a transducer, a pressure transducer that converts pressure fluctuations into voltage fluctuations. So you can measure the pressure in voltage here, and that goes to an acquisition card, and you record this. And when you do that, you find for a canary, for example, and you have those different syllables that the canary of your grandmother has, is generated by these gestures that are different for different syllables. Pa, 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 pa. The typical song of a canary is generated by pressure gestures that have specific shapes. Can a low-dimensional model reproduce this? And actually it can. So here you have just an excitatory population coupled to an inhibitory population okay, modeled in terms of rates, and modeling that with a Wilson-Cohen oscillator. That means X is the rate of spiking of this nucleus, and Y is the rate of spiking of this nucleus. Their behavior is driven by this Wilson-Cohen, where here you have a sigmoid, that is, you have for this nuclei some input, and the output is going to depend on this sigmoidal processing of the information. And when you drive this periodically with the input to the excitatory and inhibitory population with simple instructions, the response of this dynamical system has the exact shapes at the exact rates that you measure in the experiment. And this is a low-dimensional model that you don't have many parameters to play with, right? Actually, it is that when you generate a subharmonic response of certain period with this thing, the morphology has to be something specific. When you force a nonlinear dynamical system, you have subharmonic solutions where the shape is determined by the dynamics. You cannot change your parameters and get whatever shape. So we'll have a possible exercise. It's going to be to study a nonlinear oscillator, which is periodically forced, and see which different shapes of solutions you can have. You don't have that many degrees of freedom. So these are the kind of things that you also look for a model, something where you don't have so many ways of cheating. We want to model this, and you have a model that has, I don't know, 1 million parameters. Of course you will get it. Can you get a neural network that reproduces this? Of course. The real deal here is that you model it with a low-dimensional dynamical system with interpretable things that give you hope that will let you learn something about the problem. Okay. This is the kind of bifurcations that you have for the basic excitatory and inhibitory populations. So here you have the input to the inhibitory population, the input to the excitatory population. You have the different regions in parameter space with different dynamics. So if you put your system in one of these excitable regimes and you force it periodically, you get the response that you have experimentally. So Newton's mandate. First, understand the mechanics, plug that into the machinery of dynamical systems, and predict. The novelty of the 20th century was that there was a qualitative theory of dynamical systems and numerical integration as an exploratory tool. So last century, the big thing is that even if you had a complicated differential equation that didn't have an analytical solution, you have all these techniques of dynamical systems that allow you to learn something. Okay, this is basically nonlinear dynamics, which is the start of last century, if you want. But what happens if you want to understand what is extraordinarily complex? If we want to design a new medicine for some disease or stuff like that. This is where the new tools came into place, which we're going to be talking about in the next 2 classes. Artificial intelligence, which is in general this hope that we will build machines solving things that we can solve. Among those, machine learning, and within machine learning, deep learning, where if you want to summarize this, all I talked about in this first talk was about creating rules, using data to inform them or validate them, and getting answers. So I measure the pressure, I measure the tension with my experiments, I put the rules, which is the little model that I play with, and I get a song. This is the traditional approach. The new approach is you train it with examples. You have no idea what's going on. You have no hope, no aspiration of understanding what is going on. You just show them a bunch of examples, and you say, this example gave me this answer, this example gave me this answer, this example gave me this answer. And I want to feed parameters in this machine so that hopefully when I use new data, I get the right new answer. So in this case, the rules are the vector field. And in this case, sorry that this was in Spanish, so we have to construct functions which are complicated and sophisticated, and the question is how. Well, these are some of the examples that we're going to be seeing in this course. Autoencoders for achieving low-dimensional representations of data, convolutional neural networks to achieving classification, recurrent neural networks to make analysis of time series data. This is the recurrent neural network, which is the grandmother of the transformer, which is feeding your ChatGPT. Okay, so we're getting very close, if we get far enough in the course, to being very close to ChatGPT. So, what did I write there? So the question is this: how are these two paradigms related? This is something that I liked a lot because, let me tell you this, this is a personal comment. I come from nonlinear dynamics. I am very rooted in the field of dynamical systems and basic mechanisms. So when I started to read about artificial intelligence and neural networks, my first reaction was that this sucks. This, I hate it. But then I thought, maybe I'm too old, right? Maybe this is because I'm old, and old people say no to whatever is new, right? They say, well, let's try to give it a shot. So why do they work? When a neural network works, if it does the same that my dynamical system does, where did it hide it? Where did it put it? Why is a neural network doing something so good? So I found that that was an interesting question, so I'm going to be talking a little bit about that. Also, I was, during the pandemic, another thing that I was an editor in Chaos, Solitos, and Fractals with Stefano Boccaletti, and we said, let's have an issue of pandemic, so we encourage good scientific dialogue about how to model this thing, and we were expecting all these kind of SIR models and stuff like that. And we had like this 80% of articles coming from China, India, whatever, all about trying to model this with neural networks. And I said, well, I'm missing something here. So something is happening, and I'm not seeing it coming. And this was encouraging me to try to understand a little bit more about these things. So in the new two lectures that come, I try to share a little bit about that. This is a convolutional neural network. It is used for, oops. Can we put again the last one? And I'm finishing. Okay. This is a review. That is always so useful to have. The songs, the birds. Okay. Bless you. This is a convolutional neural network. This is the typical architecture that was based on our understanding of human vision that allows us to have this beautiful classification scheme that we're using for whatever, and is creating right now a profile of you when you do a like in your Instagram, X, Twitter, whatever. So you are all the time being classified and reclassified by these guys in here. And as I said, this is the recurrent neural network that basically, when you put some attention and some additional mechanism, is creating the transformers. So in the next two classes, I'm going to be using examples of this to see how you use them, and a little bit try to relate them and see what they have in common, what they do when a neural network does their stuff, where they're coding their knowledge of the dynamics and so on. And with this, we have 12 minutes, almost 15, for questions. Thank you very much.
Thank you very much, Gabriel, for the wonderful lecture.
Hi, Gab. Do you need to know the biophysics of the ear also?
Of the?
Of the ear, of the biophysics, the parameters for the ear. Does the ear also learn things?
Oh, that's so I don't work on that. I don't work on that. But there is a beautiful biophysics of the ear that is involved in here, because the way in which you process your input is first decoded by the ear mechanism, and how the cochlea is processing the information and then coding it in all the auditory part. I don't work on it, but yes, in order to do it and do a good model of the learning, you have to include the processing of the hearing. Yes.
Does it learn? Does the ear get better? I mean,
Not that I know. You do learn how to code aspects of the result of the processing, but the first stages of the hearing process, I think there is no learning involved. But I'm not an expert, so let me think a little bit more. I know exactly whom to ask, but I think that in the first stages you don't learn.
Yeah, I had another question, but now that he asked about the learning, do they forget when they get old?
Okay, so it depends on the species. So some species, what they have is they have neurogenesis, for example, canaries, and every year, what they have is new neurons that come and get reattached to the brain and allow them to incorporate new syllables. So yes, they change the repertoire. Some species change the repertoire, and when they are incorporating new neurons, they stop using other circuits. They modify them. Many species, though, learn only one song, and this the only thing that they will sing until they die.
Okay. Can I ask another question? This was really the question, actually.
So just one thing. In the natural world, there aren't many examples of birds that have been followed for many years. The oldest bird that has been followed is 70 years old, but belongs to a species that sings very poorly. So in no-sign birds, you don't have birds that have been followed for so many years. So I even doubt whether it's a thoroughly studied phenomenon. Yeah.
Cool. Yeah. About the model, in the model you showed you were modeling the vibration of the labia, right?
Right.
How do you get the sound from that?
Okay. So once that you have the motion of the labia, you have the airflow, because the airflow is the velocity of the air that is passing through you times the area. So this generates a rate of mass injection of air into the trachea, because you have the density, the velocity of the area, and that gives you the mass that passes per amount of time. You take the derivative of that, and the rate of the derivative of the rate of a mass injection is the definition of the sound. Is how fast it changes the amount of mass that you're putting per amount of time. So you use the area plus the velocity that you computed, because it's basically proportional to the air sac pressure, okay? And you take the derivative of this quantity.
Okay, cool, thank you.
I was going to ask other thing, but just related to that question, what is the role of having two tubes, like from two lungs?
So this is very interesting. So some species use one side to generate high-frequency sound and the other one for low-frequency sound. Like, for example, for a canary, you can start at 7 kilohertz and up to 35 kilohertz you created with the right sound. And then in the other one, you can continue with more relaxed instructions and have from 3.5 kilohertz to 700 hertz and so on. So you can increase that, or you can have more complex sounds. So sometimes they sing simultaneously with the two sides, and they generate more complicated sounds. Whether that is interesting or not to a female, I don't know. So I don't know which would be behaviorally the advantage of creating more rich and complicated songs, but they use it to generate simultaneously a very rich sound.
Cool. And just about this next point that you mentioned about this change of paradigms, that you started your career on nonlinear dynamics, and now you are a bit of a step behind on going into AIs and such. And is it the same change of paradigm when you go from nonlinear dynamics in very deterministic systems to statistical physics, and you have a completely different way of describing your system? Is it the same change? I don't think it is, but I have no idea of the answer.
So let me tell you this. I started doing nonlinear dynamics, and then I went to my first job that was a fluid thing. And then I liked very much a girl who was an astrophysicist, so I started to work in astrophysics for a while. So I wanted to interact with her. And then I went back to a place where I got the job as a laser physicist. So I started to work in laser physics. And finally, when I put my lab, I got tired of all this and I started to work with biology. I've been working with biology for 25 years, asking money to biologists, directing students in biology, publishing in biology and in physics. So I have a wide experience in trying with different techniques and speaking different languages. This is different. Artificial intelligence and using these data science techniques doesn't compare to doing interpretable science in other disciplines. You talk to a biologist, and if you come from physics, you think that you're never going to find a common language and that you're going to kill each other. Basically, you will hate it with. But then you will realize that you are two natural scientists who want to understand mechanisms. And then you're going to be talking to a data scientist, and then you will see that this is completely different. So I think it's very different. We're talking about something completely different here, whose scope I cannot predict. But this is something else. It's my opinion, my humble opinion.
Wonderful talk.
Thank you.
Fantastic. Thank you so much. I would like to hear your comments, because one thing is to go from machine learning all the way to deep learning, and sometimes you get just very correct answers.
Right.
But how would you go back to have some interpretability, some insights that human can understand? Okay,
Right.
because just a black box sometimes it's too vague sometimes, because you say, well, why? It's like a dogma or
Exactly.
whatever.
Yeah.
So could you comment on that?
Yes. Let me tell you my experience with that. For example, I think I will talk a little bit about this, but I'm not sure. I have to review my slides, but it might be the case. For example, in the case of an autoencoder. In an autoencoder, what you do is basically you present some result and you want to copy it, but you urge the system to compress the information in here. No? The idea is that to get a reduction of the dimensionality of the problem. In that case, for example, we have shown that if you are processing some images whose underlying dynamics is a dynamical system with a flow with certain topology, then you can prove mathematically that in here you have something that is topologically equivalent, that this processing is an actual embedding of the dynamics, for example. So if you go in there, what you are getting is a deformed version of the original phase space that was underlying the dynamics, for example. And in a recurrent neural network, basically the processing here is done by some hidden units. And for this I have a mathematical proof. For this I don't, but I do have lots of compelling data that in the hidden units we also have an embedding of the dynamics. So topologically you have something that is completely equivalent to the original flow. So I think that if you look in the right places of this, you can learn about the underlying phase space that is controlling the dynamics of your problem. So this would be a hint for me in order to get something back out of the processing. Not only the machine that allows you to do the processing, but to use the information that you coded in here to learn about the dynamics that was underlying. So I think you can, but no one is paying attention to that, but you can. And I think this is a quite fascinating field for applied math, I think. Of course, since you didn't design it to do it, you will have it in a representation that is completely mixing all the pertinent variables, but you will get a representation of what happens in the phase space. So I still have hope that there is a way of using these things to understand something, but they are not designed to do that. So, and if you want to see in here, there are some people that do the equivalent of in convolutional neural networks. They do some poking into the different layers to try to understand how they have been processing it. Because in here, they have copied the neural architecture of vision. And the only thing that is understood is that in the first layers, you find the shapes of stuff and so on. How they will be building the most abstract components to be able to classify We don't know. And what some people are doing is doing the equivalent of neuroscience of poking these units in there and try to do neuroscience of the neural network. For this one, I have no answers. I don't have intuitions either. But for this and this, I do, and I plan to share that in this course.
It's not much of a question. It's more like it's kind of a question and a suggestion, and it also ties into the previous question about the interpretability of the neural networks. There's a class of it's a recent development in neural networks for dynamical systems called physics-informed neural networks.
Yes,
and,
of course.
Neural operators.
Yes, exactly.
It seems to be a perfect use.
Exactly. Yeah, in some. Well, that's a nice example. So one way in which people have been using these neural networks is to fit something that is your previous perception of the model, and in the loss, that means in the computation of the difference in between what you are expecting and what you are getting in the loss, instead of just comparing the result, the expected result with the result that you get, you also put something that weights the departure from a model that you conjecture. And when you fit the parameters of the dynamical system. And in that way, thank you for reminding me of that. Using these physics-informed neural networks that measuring the loss, the difference in between your model and what you're getting, you get a way of interpreting or at least fitting your prejudice or your conjecture of a dynamical system. That's another way in which people have been using this to understand a dynamical problem.
Hi.
Thank you for that.
I was thinking about the natural variability that you have between birds from the same species. I think that you could have a contribution from their physical bodies, the size of the lungs,
Yes.
the muscles, but there is also a change on the capability of learning and how they can perform the sound that they listen. Can you quantify or try to understand how much of each contributes for their sound that they produce?
So those are very difficult experiments to do. So for example, we're doing right now with a student called Roberto Vistel an experiment where we're testing the responses of wild birds to synthesis where the skill of the bird is tested. So we want to find whether freak is sexy, basically. This would be the question. Whether if you have someone that excels more than the best fitted birds in some particular skill are more attractive for the females, but we still don't have the process results. And those are very difficult experiments to do because when you work with wild birds, you have to process thousands of protocols together to get sensible numbers. So for example, we've been getting 1,500 protocols played to different birds last year, which we still didn't process, and we still don't have enough precision to get significant results. But it's a beautiful set of experiments that I like very much. So I particularly have the same prejudice that you have, that skillful learning is sexy, at least in ocine birds, more than size and stuff like that.
Gabriel, thank you so much for the talk. This is a really exciting topic. I was wondering, when you posed the question on what is the importance of having mechanistic models for these things, I was wondering that when you have a mechanistic model, you can use it as a tool and use this in other types of areas in ecology, for instance, and study the evolutionary dynamics of these kind of things. I think this relates a little bit to the question that Nathan asked about the hearing, but have you thought about trying to understand this coordination game of male and female trying to identify and separate them through time?
No, it's a beautiful question. I haven't thought of doing it, but it's a beautiful question. Yeah, thank you for that. Yeah.
Thank you. Maybe a follow-up question on this kind of things. Have you, in your experience, could you give some insights on how to communicate and have proactive and prolific collaborations with throughout areas to join in physics, biology, math.
Okay, so well, that's a very interesting question. I always say this sentence, so whoever is here and has heard me before, sorry because I'm repeating myself, but when I started to collaborate with biologists, I thought that the problem was they don't know mathematics, we have no hope. And probably I'm sure they were thinking, this guy has no idea of biology, this collaboration has no hope. I think that's not the problem. So in general, biologists can learn the mathematics and physicists can learn the biology. What is difficult, very difficult, is in particular in biology and physics, is that physics has built its cultural power on simplification. You tried, I mean, you are a cool physicist if you use 1 or 2 equations. If you are a physicist with 15 equations, you go to talk on Friday afternoon. And if you have like 2 equations, you talk on Monday morning, right? This is basically a caricature, but typically this is what happens for a physicist. Now, for a biologist, being rigorous is to put everything in the framework of evolution. And in evolution, is not a stupid detail. Something in evolution that happened there happened in a context and is responsible for that species surviving today in a complex network and in a complex history. So when you come and you simplify a biological problem, it's not that you, they don't think that you are forgetting about the little details. You don't understand evolution. So the problem is to understand that you have 2 different cultures that think that being rigorous is something different. For us to understand basic mechanisms and put a hierarchy of importance of things, and I sympathize with that view, and for a biologist, unless you prove me how that lets me understand something in the framework of evolution, this is bullshit. So the problem is to understand the other. Once that you understand that the other person is not responding to you for his or her ignorance, but because of his or her search for rigor, and you respect that, then you can have a fruitful communication. But it's about respect and understanding the complexity of 2 different cultures. So I think that a lot of modesty is necessary for physicists in particular that have so many quantitative tools. Usually they look down at biologists like some people that don't know mathematics. And biologists have huge grants, and they think of physicists as just computational slaves that, you know, they have to put some equations to look nice, your presentation. If you approach either of the 2 with that attitude, you will never collaborate. You have to understand what is important for the other with respect. So the key would be respect, I would say. And understanding history of science, which have 2 huge guys, because Darwin and Newton are 2 equally huge guys.
Okay, just one last question, if I may, myself. What do you think is the evolutionary mechanism behind having these 2 large groups of species? One where the physics is the same and the other one where every species is different.
Well, let me tell you that I think about that a lot and I don't know the answer. So because I don't know if it's yours, but my prejudice was always that learning is an evolutionary advantage and you would see learning taking over different species, and that's not how it works. So, I don't know, in the complexity of adaptation and evolution, how that plays, I don't know. And I think about that all the time, but I have nothing interesting to say. So sorry.
That's fine. That was wonderful. Thank you very much. So, we have coffee break now.